Somewhere in your childhood, you asked the largest question a person can ask. If everything came from the Big Bang, what came before it? And if there was nothing before, where did the nothing come from? An adult probably told you, gently, that it wasn't a question that made sense, and then changed the subject. Tonight I want to tell you that the dodge you were given was, in its own way, the most honest thing anyone ever said about the universe. Because the people who study this for a living say something almost identical, only with far more mathematics attached. The word nothing, it turns out, hides a trap. So settle in, get comfortable, and let me show you what physics found inside it. Part 1. The question you were told not to ask. Somewhere in your childhood, you almost certainly asked the largest question a person can ask. Maybe you were lying in the back of a car at night, watching the streetlights slide by, or maybe you were staring at the ceiling, unable to sleep, the way you might be right now. And the question arrived on its own, uninvited, the way the best questions always do. If everything came from the Big Bang, what came before the Big Bang? And if there was nothing before it, then where did the nothing come from? You probably asked an adult, and the adult, if they were honest, gave you some version of the same gentle answer everyone gives. They told you it wasn't really a question that made sense. They told you the beginning was the beginning, and you can't go back past the start. And then they probably changed the subject, because the look on your face was getting a little too serious for bedtime. I want to tell you something tonight that might keep you up a little longer, in the best possible way. That deflection you were given as a child, that quiet little dodge, was not a failure of imagination. It was, in its own way, one of the most honest things anyone has ever told you about the universe. Because the people who study this for a living, the cosmologists and the theoretical physicists, who have spent entire careers staring into the first instant of everything, will tell you something almost identical, only with far more mathematics attached. They will tell you that the question hides a trap, two traps actually, and they are buried inside two small and innocent-looking words. The title of what we're exploring tonight is a simple one. Did the universe start from nothing? 5 words. A child could ask it, and a child has. And yet I promise you that by the time we are done, you will see that almost none of those 5 words mean what you think they mean. The word that will give us the most trouble is the word nothing. And right behind it, just as slippery, is the word start. We are going to take both of them apart slowly, the way you might take apart an old clock just to see what makes it tick. And what we find inside is going to be far stranger than the simple story you were taught. Let me start with why this question feels impossible. There is an idea so old that it predates almost all of recorded science, an idea the ancient Greek thinker Parmenides put into words more than 2,000 years ago. Nothing comes from nothing. In Latin, it became a kind of motto for the whole of rational thought. Ex nihilo nihil fit. Out of nothing, nothing comes. It feels less like a scientific claim and more like a basic rule of being alive. You have never once watched something appear from genuine emptiness. Your entire experience of reality, every single moment of it, has taught you that things come from other things. A tree comes from a seed. A fire comes from a spark. A child comes from its parents. Cause leads to effect, and every effect you have ever witnessed had a cause sitting right behind it. So when someone says the entire universe, all of it, every galaxy and every grain of sand, came from nothing at all, your mind does something very reasonable. It refuses. But here is the trouble, and it's the reason this question has haunted thoughtful people for thousands of years. The other option is just as impossible to swallow. If the universe did not come from nothing, then something was always here. Something existed forever, with no beginning, stretching infinitely far into the past. And when you really try to picture that, an endless backward chain of moments with no first link, your mind refuses that too. An infinite past feels just as absurd as a creation from emptiness. So we are caught. Both answers break our intuition. Either something came from nothing, which seems to violate the most basic rule we know, or something has simply always existed, which seems to violate our sense that everything needs an origin. There is no comfortable third door. Or at least, there doesn't seem to be. Hold on to that thought, because finding a third door is, in a way, what the last 100 years of physics has secretly been about. Now I want to do something with you. Before we go any further, I want you to actually try to picture nothing. Not empty space, not a dark, quiet room, to real nothing. No air, no light, no walls, no room, no space for a room to be in, no time for the nothing to last. Take away the stars, take away the void between the stars, take away the void itself, take away up and down, here and there, before and after. Try to hold that in your mind for even a single second. You can't. Nobody can. The moment you imagine nothing, you have imagined a kind of empty space, a black stage with the lights off, and that black stage is already something. It has dimensions. It has a place where things could go. The truth is that the human mind may simply be incapable of picturing genuine nothing, because every thought we have is built out of somethings. And if we cannot even picture it, we should at least be suspicious that we know what we mean when we casually say the universe came from it. This is the quiet scandal at the center of tonight's question, and it's the thread I want you to follow with me all the way to the end. We are going to discover that physics, over the last century, did not so much answer the question, did the universe come from nothing? Instead, it did something sneakier and far more interesting. It redefined the words. It looked at the word nothing and discovered that nothing, in the only sense we can actually study, is not empty at all. It looked at the word start and discovered that the start may not be a start. And by the time both of those words have been turned inside out, the original question doesn't get a clean yes or a clean no. It gets transformed into something you would never have expected. The question doesn't get answered. It dissolves. I know that sounds like a cheat. It sounds like the grown-up changing the subject all over again. But stay with me, because the way it dissolves is genuinely beautiful, and it tells us something profound about the universe, and, strange as it sounds, about you. Tonight, we are going to walk this slowly. First, we'll make sure the question even gets off the ground by asking how we know there was a beginning at all, because remarkably, we do know that much. Then we'll spend a long, patient stretch taking apart that first dangerous word, nothing, and you'll see why physicists say it has the same energy, the same balance sheet as an entire universe. After that, we'll turn to the second word, start, and we'll meet a parade of ideas in which the universe never truly started so much as it changed, bounced, budded, or tunneled into being. And finally, we'll arrive at the strangest possibility of all, that the question itself was malformed from the very first word. So, get comfortable. Let the weight settle out of your shoulders. There is nowhere we need to be, and nothing we need to solve in a hurry. We have all night, and the universe has had 13.8 billion years, so a little patience is the least we can offer it. Before we can ask what came before the beginning, though, we have to be sure there was a beginning to come before. And it turns out that is the one part of this entire story we are genuinely certain about, is less than break time equals 1s, is greater than number. Part 2. How we know there was a beginning at all. It would be reasonable, at this point, to wonder whether the whole idea of a beginning is just a story we tell ourselves. Maybe the universe is simply eternal and unchanging, the same forever, and the notion of a Big Bang is a human myth dressed up in equations. For a long time, Many serious scientists thought exactly that. So before we go chasing the origin, we should pause and ask the fair question. How do we actually know the universe had a beginning at all? And the answer is one of the great detective stories of science, built from 3 separate clues that all point in the same direction. The first clue arrived in the year 1929, when an astronomer named Edwin Hubble was measuring the light from distant galaxies. He noticed something that, at first, made very little sense. Almost every galaxy he looked at was moving away from us. And not only that, the farther away a galaxy was, the faster it was fleeing. Now, your first instinct might be that this puts us at the center of some great explosion, with everything rushing away from our special spot. But that is not what it means at all. The correct picture is far stranger and far more elegant. Space itself is stretching. Imagine a loaf of raisin bread rising in the oven. Every raisin moves away from every other raisin, not because the raisins are traveling through the dough, but because the dough between them is expanding. From the point of view of any single raisin, all the others appear to flee, and the most distant ones flee fastest. The galaxies are the raisins, and space is the dough, and the whole thing is swelling. Once you accept that space is expanding, a simple and irresistible logic takes over. If everything is spreading apart today, then yesterday it was all a little closer together. And the day before that, closer still. Run the film backward, frame by frame, and the galaxies crowd in toward one another. Keep running it back, billions of years, and everything that exists is squeezed into a region smaller and smaller, hotter and hotter, denser and denser, until the entire observable universe is compressed into something almost unimaginably tiny and almost unimaginably hot. That rewind has a logical endpoint, a moment when the density and temperature climb toward the limits of what our equations can describe. We call that moment the Big Bang. So the expansion we see today is itself the first piece of evidence that there was a hot, dense origin. The second clue is, to my mind, the most beautiful, partly because of how it was found. In the year 1964, 2 scientists named Arno Penzias and Robert Wilson were working with a large horn-shaped antenna at Bell Labs in New Jersey. They kept picking up a faint hiss, a background noise that would not go away no matter where they pointed the instrument. It came from every direction in the sky, day and night, all year round. They were so convinced it was a fault that they climbed inside the antenna and scrubbed out the droppings left by a pair of pigeons that had been roosting there, certain the mess was the source of the noise. The hiss remained. What they had stumbled onto, by accident, while cleaning up after birds, was the afterglow of the Big Bang itself. We call it the cosmic microwave background. It is the light left over from when the entire universe was a glowing, white-hot fog, and it has been travelling toward us for nearly 14 billion years, stretched and cooled by the expansion of space, until it now sits at a temperature of just 2.7 degrees above absolute zero. That faint glow fills all of space, and it is, quite literally, the oldest light there is. You have actually seen it yourself, in a way. A tiny fraction of the static on an old, untuned television set was this very signal, the breath of the early universe whispering through your living room. The third clue is hidden in the simplest substances in existence. When the universe was only a few minutes old, far too hot for atoms to hold together but cool enough for the first atomic nuclei to form, it ran a kind of cosmic cooking experiment. The physics of that early furnace predicts a very specific recipe. For every measure of helium that forms, there should be about 3 measures of hydrogen, roughly 3/4 hydrogen, 1/4 helium, with the faintest pinch of a few lighter elements. And when we look out at the oldest, most pristine clouds of gas in the universe, the ones that have never been cooked inside a star, that is exactly the ratio we find. The universe wears the fingerprints of its own first minutes, and those fingerprints match the prediction precisely. 3 clues: the expansion of space, the afterglow in the sky, and the recipe of the lightest elements. Together, they let us say something with real confidence. The universe was once hot, dense, and tiny, and from that state, it has been expanding and cooling for about 13.8 billion years. There genuinely was a beginning event, a moment we can point back to. But here is where I have to be very careful with you, because this is exactly the kind of place where the story usually gets oversold. All of this evidence tells us that there was a transition, a hot, dense origin we can rewind to. It does not, on its own, tell us that the universe came from nothing. It only tells us how far back our clear vision reaches before the fog closes in. We have found the edge of the map. What we have not done is prove that there is nothing beyond it. And that gap between knowing there was a beginning event and knowing whether that event was a true start or merely a handoff from something else is precisely the ambiguity living inside the word start. We will spend the rest of tonight inside that gap. But first, we have to visit the place where the map runs out entirely, the place where our finest equations stop making sense and begin, instead, to scream. Is less than break time equals 1 is greater than number, part 3, the place where the math screams. To understand what happens at the very beginning, you have to understand the tool we use to describe it, and that tool is Albert Einstein's theory of general relativity. Now, you have probably heard that relativity is about gravity, and that's true, but the way it describes gravity is the part that matters for us tonight. Einstein realized that gravity is not really a force in the way we usually think of forces, not a rope pulling planets toward the Sunday. Instead, gravity is the bending of space and time themselves. A massive object like a star sits in space-time the way a heavy ball sits on a stretched rubber sheet, and it creates a curve, a dip, and everything nearby rolls along that curve. The Earth orbits the Sun not because it is tied to it, but because it is following the straightest possible path through curved space. Matter tells space how to bend, and bent space tells matter how to move. That is general relativity in a single breath, and for over a century it has passed every test we have ever thrown at it. So naturally, when physicists wanted to understand the beginning of the universe, they took these equations and ran them backward in time, just as we did with the expanding galaxies, but now with the full machinery of relativity switched on. And as they ran the clock back toward that first moment, something disturbing happened to the numbers. As the universe shrank toward zero size, the density of everything inside it began to climb. And it did not climb toward some very large but sensible number. It climbed toward infinity. The curvature of space-time, the bending, climbed toward infinity as well. At the moment we label time 0, the equations of general relativity output a quantity that is infinite, a point of infinite density and infinite curvature crammed into zero volume. Physicists have a name for this. They call it a singularity. Now, I want to slow down here because this is one of the most misunderstood ideas in all of science, and getting it right is essential to everything that follows. When you hear that the universe began as a singularity, a single point of infinite density, it is very natural to picture a tiny, intensely bright dot of stuff, sitting alone in a black emptiness, which then exploded outward to become everything. That picture is burned into popular imagination, and it is wrong. It is wrong in a way that matters enormously for our question tonight. Here is the truth. Infinity is not a real, physical answer. In physics, when your equation produces infinity, it is almost never telling you that something in nature is genuinely infinite. It is telling you that your equation has stopped working. The infinity is not a feature of reality. It is an error message. Think of what happens if you take a simple calculator and try to divide a number by 0. The screen does not show you the true answer because there is no true answer. Instead, it flashes up an error, a little signal that says you have asked me to do something outside the rules I understand. The singularity at the beginning of the universe is that same error message written in the language of space-time. It is the universe's way of telling us that general relativity, our magnificent, century-defying theory of gravity, simply does not apply in the conditions of the first instant. The theory breaks. It hands in its resignation. This was made rigorous in the 1960s and 70s by two of the finest minds in the field, Roger Penrose and Stephen Hawking. Working with the mathematics of general relativity, they proved a set of results now known as the singularity theorems. What they showed was that, given the rules of classical general relativity and some very reasonable assumptions about how matter behaves, a singularity in the past was not some avoidable accident. It was unavoidable. If general relativity is the whole story, then the universe must begin at a singularity. But notice the careful phrasing. If general relativity is the whole story, Penrose and Hawking did not prove that a singularity really existed. They proved something subtler and, in a way, more useful. They proved that general relativity, taken all by itself, demands a singularity, which is the same as proving that general relativity, taken all by itself, must be incomplete. A theory that predicts its own breakdown is a theory waving a flag, telling you that something deeper is needed exactly where it fails, and this completely reshapes our question. The popular image of the universe starting from nothing usually rests on this idea of a point appearing in an empty void and blowing up, but that image is built on top of a broken equation. The singularity is not a thing that existed in the nothing and then exploded. It is the symbol that marks where our knowledge currently ends. So when we ask whether the universe came from nothing, we are really asking about a region of reality where our best theory of space, time, and gravity has thrown up its hands. To get any further, we need a new kind of physics, one that takes over precisely where general relativity dies. And we happen to know where to look, because there is a second great theory in physics, one that rules the realm of the unimaginably small, and the beginning of the universe was nothing if not small. How small? At the very first instant, the entire observable universe, everything that would one day become 2 trillion galaxies, was packed into a region governed by what we call the Planck scale. The Planck length is the size at which space and time themselves are thought to become grainy and uncertain, where gravity and quantum mechanics must finally be combined. To give you a sense of just how small that is, consider this comparison. If you took a single proton, one of the particles inside the nucleus of an atom, already a thing so small that trillions would fit inside the period at the end of a sentence, and you asked how the proton compares in size to the Planck length, the answer is roughly the same as how the entire solar system compares to that proton. The proton is to the Planck length as the solar system is to the proton. That is the scale of the early universe. That is the regime where our familiar physics dissolves and the quantum world takes command. And the quantum world has its own radical, almost heretical idea about what nothing really is. To follow the question any further, we have to leave the comfortable world of bending rubber sheets behind and step into the place where empty space turns out to be the busiest place of all. Is less than break time equals 1s is greater than number, part 4. Nothing is not empty. I want you to picture a box, an ordinary box, sitting in front of you. Now reach in and take out everything inside it. Take out the objects, take out the air, take out every last molecule of gas until not a single particle remains. Then go further. Take out the light passing through it, every photon, until it is perfectly dark inside. You have now created what most people would call a perfect vacuum, a box of pure nothing. And here is the discovery that overturned 300 years of intuition, the discovery that sits at the center of our question tonight. That box is not empty. It is, in fact, one of the busiest places you could possibly imagine. It is seething. To understand why, we have to meet one of the strangest rules in all of physics, a rule discovered by Werner Heisenberg in the 1920s. It is called the uncertainty principle, and most people have heard of the version that says you cannot know both the position and the speed of a particle at the same time. But there is another version of it, and this is the one that matters for the vacuum. It says that you cannot simultaneously know, with perfect precision, both the amount of energy in a region and the exact moment in time you are measuring it. The two are linked, and the link has teeth. Over very short intervals of time, the energy of empty space is not fixed at zero. It is fundamentally fuzzy, blurred, uncertain, and nature exploits that fuzziness in a remarkable way. Because the energy of a tiny region of space is uncertain over short times, particles are allowed to briefly borrow energy from the vacuum and pop into existence, so long as they pay the debt back almost immediately. They appear in pairs, a particle and its mirror image antiparticle, born together out of the fluctuating energy of the vacuum, and then, a fantastically brief instant later, they find each other again and annihilate, vanishing back into the nothing they came from. This is happening everywhere, all the time, in every cubic inch of what we call empty space. Right now, in the few inches of air in front of your face, and just as much in the empty space behind the farthest galaxy, particles are flickering into being and winking back out, an endless, silent froth. Physicists call them virtual particles, and the froth they create is the reason we say the vacuum is the lowest energy state, but it is most certainly not the zero energy state. There is a flaw, and the flaw is alive. Now, I can already hear the reasonable objection forming in your mind. This all sounds like a lovely mathematical fairy tale, you might think, but how could anyone possibly know it's real? You cannot see a virtual particle. They are gone before any instrument could catch them. And this is where physics earns its keep, because there is a way to feel the froth even if you cannot see it. And it was predicted by a Dutch physicist named Hendrik Casimir in the year 1948. Casimir reasoned as follows. If empty space is full of fluctuations, of these fleeting waves of energy, then imagine placing two flat metal plates extremely close together, facing each other in a vacuum. Between the plates, only fluctuations of certain sizes can fit, like the limited notes a short guitar string can play. But outside the plates, in the open vacuum, fluctuations of every possible size are allowed. That means there are slightly more of these vacuum fluctuations pushing on the plates from the outside than from the inside. The result is a real, physical force pressing the two plates together, a push that comes from nothing but the structure of empty space itself. For decades, this remained a beautiful prediction. Then, in the year 1997, a physicist named Steve Lamoureux measured it directly in the laboratory, and the force was exactly the size Casimir's equations had foretold. Read that again and let it settle, because it is one of the most quietly astonishing facts in science. Two ordinary metal plates, holding no charge, sitting in a vacuum, are pushed together by the pressure of empty space. Nothing is pushing on them, and yet they move. The nothing has a structure, the nothing exerts a force, and in more recent years, this picture has only grown sharper. In 2025, researchers, using carefully designed simulations and experiments, managed to coax actual light, real photons, out of the vacuum by stirring its fluctuations, producing something from what looks for all the world like nothing. The seething sea is not a metaphor. It is the flaw of physical reality. So now we can return to our question with new eyes, and you can already feel the trap in the title beginning to spring. When a physicist stands up and says the universe came from nothing, what do they very often mean by that word nothing? They do not usually mean the philosopher's absolute void, the total absence of everything. They mean this. They mean the quantum vacuum, this restless, energetic, law-governed sea of fluctuating fields. And that kind of nothing already contains a great deal. It contains quantum fields stretching through it. It contains the laws of physics that govern how those fields behave. It contains energy, real and measurable energy. So, in a very real sense, the moment we look closely, the word nothing in our title quietly transforms into a very particular and very busy kind of something. This is not a trivial point, and to its great credit, physics has not tried to hide the difficulty. There is a famous and genuinely valuable argument on exactly this question between the physicist Lawrence Krauss, who wrote a book arguing that the universe could arise from nothing through quantum processes, and the philosopher David Albert, who pushed back hard. Albert's objection cuts right to the bone of our question. A quantum vacuum, he pointed out, full of fields and governed by the laws of quantum mechanics, is simply not nothing. It is something, and a rather elaborate something at that. To explain how a universe arises from the quantum vacuum is a magnificent achievement, but it is not the same as explaining how something arises from genuine, absolute nothingness, the kind with no space, no time, no fields, and no laws. And here both sides are, in their own way, telling us something true. Krauss is right that physics can describe a universe emerging from the vacuum. Albert is right that the vacuum is not truly nothing. They are not really disagreeing about the physics. They are disagreeing about which thing the word nothing is allowed to point at. And this opens up the most vertiginous possibility of the entire evening, one I want you to hold gently in your mind as we go forward. It may be that genuine nothing, the absolute void with no laws and no fields at all, is permanently beyond the reach of physics. Not because we are not clever enough yet, but for a structural reason. Physics works by writing down laws. Every theory we have ever built, every equation, begins by assuming that something behaves according to some rule. The instant you have a rule, you have a kind of something. So, when we try to use physics to reach back to true nothing, we always find that we have smuggled a law in with us. We carry our somethings on our backs. We may never be able to describe the absolute void, because the very act of describing requires a structure that the void, by definition, does not have. The froth in the box may be as close to nothing as physics is ever permitted to get. There is one more twist to the energy of the vacuum that I cannot resist sharing, because it is at once one of the greatest triumphs and one of the greatest embarrassments in all of physics. If empty space has energy, then that energy should have a gravitational effect. It should, in fact, push space apart, acting like a kind of anti-gravity built into the vacuum itself. And astonishingly, we have discovered that something exactly like this is real. In the late 1990s, astronomers found that the expansion of the universe is not slowing down, as everyone expected, but speeding up, accelerating, as if some unseen energy in empty space were pushing the cosmos apart. We call it dark energy, and the simplest explanation is that it is the energy of the vacuum itself. So the seething nothing is not only real, it appears to be the dominant force shaping the future of the universe. But here is the embarrassment. When physicists try to calculate how much energy the quantum vacuum should contain, by adding up all those flickering fluctuations, they get a number that is too large, not by a little, but by a factor with something like 120 zeros after it. It is the worst prediction in the history of science, a mismatch so enormous it is almost comical, and yet it tells us something humbling and important. We know the nothing has energy. We can even measure its effect on the whole cosmos. But we do not yet understand the nothing nearly well enough to predict how much energy it should have. The floor of reality is alive, and it is still keeping secrets. So that is the first half of our answer taking shape, and it already changes everything. The nothing in our title is not an empty stage waiting for a universe to appear on it. It is a seething quantum sea with energy and law woven through it, and virtual particles flicker through that sea for spans of time so short, around 1,000th of a billionth of a billionth of a second, that they never register on any clock you could build. But this only deepens the mystery in the most wonderful way. Because if empty space is not empty, if the vacuum is brimming with energy, then a truly outrageous question becomes possible to ask. Could you get a whole universe's worth of energy out of that vacuum? Could everything, every star, and every galaxy have come out of the nothing for free, without breaking a single law of physics? It sounds absurd, and yet the books may balance perfectly. Let me show you how. Is less than break time equals 1s is greater than number. Part 5. The free lunch. There is a rule in physics that most people have heard of, even if they have never seen it written down, and it feels as solid as any rule could be. Energy cannot be created or destroyed. It only changes form. You cannot get something for nothing. This is the law of conservation of energy, and it is one of the most thoroughly tested principles we have. So, at first glance, it seems to slam the door on our entire question. If energy cannot be created, then how could the enormous energy of an entire universe, locked up in all that matter, simply come into existence? Where would it possibly come from? It would be the ultimate violation, the biggest free lunch in history, and physics does not believe in free lunches. Except that, when you look very carefully, the universe may be exactly that. And the trick lies in a kind of energy we usually forget to count. To see it, we have to talk about gravity, but in a way you may never have considered. We always think of energy as a positive thing. The energy in a battery, the energy in a moving car, the energy locked inside matter through Einstein's famous equation relating mass and the speed of light. All positive, all on the credit side of the ledger. But gravity introduces something we do not usually think about. Gravitational energy is negative. Let me make that concrete. Imagine two objects floating far apart in space, with nothing pulling them together yet. Now let gravity draw them in toward each other. As they fall together, they pick up speed, they gain energy of motion, seemingly from nowhere. Where did that energy come from? The answer is that the gravitational field itself went into deficit. To pull the objects apart again, back to where they started, you would have to put energy in. So a system of things bound together by gravity sits in a kind of energy debt, an energetic hole. The closer and more tightly bound things are, the deeper the debt. Gravity, in the language of the ledger, is a liability. It is energy owed. Now, hold those two ideas together, the positive energy of all matter and the negative energy of gravity, and ask the audacious question that physicists began asking seriously back in the 1970s. What is the total? If you add up all the positive energy in the universe, every bit of matter, every photon, and then you add up all the negative gravitational energy, every attraction between every pair of objects across all of space, what do the books say at the bottom of the page? And the astonishing, almost unbelievable answer that emerges from the equations is that the total may be very close to zero. The enormous positive energy of all the matter in existence may be almost exactly cancelled out by the enormous negative energy of gravity. The credit and the debt may balance to nothing. A physicist named Edward Tryon proposed this idea formally in the year 1973, suggesting that our entire universe might be a fluctuation in which the total energy is zero. And Stephen Hawking, who had a gift for putting profound ideas into ordinary words, summed it up in a single, unforgettable line. He called the universe the ultimate free lunch. Because if the total energy of the universe is zero, then creating a universe does not violate the conservation of energy at all. You are not making energy out of nothing. You are separating zero into a large positive piece and a large negative piece, the way you might dig a hole in flat ground. Before you dig, the ground is level. After you dig, you have a pile of earth, which is your matter, sitting beside a hole of exactly the same size, which is your gravity. You created a mountain and a valley, something genuinely new, and yet the total amount of earth never changed. The ground was flat to begin with, and the books still balance. And it goes further than just energy, in a way that makes the whole thing even more haunting. Energy is not the only quantity that nature insists on conserving. There is electric charge. There is momentum, the quantity of motion. There is angular momentum, the quantity of spin. For each of these, the universe keeps a strict accounting, and none of them can simply be created from nothing. So you might think these other conservation laws would block the creation of a universe even if the energy balances. But here is the remarkable thing. When physicists tot up these other quantities for a closed universe as a whole, they keep finding the same answer. The total electric charge of the universe appears to be zero, every positive charge balanced by a negative one. The total momentum appears to be zero. The total angular momentum, the net spin of everything, also appears to balance out to zero. Every conserved quantity that nature watches over so jealously seems, when you sum it across the entire cosmos, to come out to exactly nothing. Now sit with what that means, because it is the strangest accounting in all of science, and it brings us right back to the central thread of our question. Every quantity that distinguishes a universe from nothing, when summed over the whole of that universe, may be precisely zero. Zero total energy, zero total charge, zero total momentum, zero total spin. Which is to say, the universe, taken as a single object, may carry exactly the same set of conserved quantities as empty nothingness. On the cosmic balance sheet, a universe and a void may be indistinguishable. They may be two different ways of writing down the very same total. And if that is true, then the transition from nothing to everything is not the violent, impossible, law-breaking act it first appears to be. It is more like a separation, a sorting, the splitting of a perfect zero into matched halves of plus and minus that, added back together, would vanish without a trace. I have to be honest with you here, because honesty is the whole point of doing this carefully rather than sensationally. This idea of the zero-energy universe is taken seriously, but it is not a settled, proven fact, and there are real subtleties. Whether the total energy comes out exactly to zero depends sensitively on the overall shape and geometry of the universe, and it works most cleanly in what physicists call a closed or flat universe. There is also a genuine technical wrinkle, which is that, in general relativity, the total energy of the entire universe is a slippery thing to even define, because energy and the curvature of space are tangled together in ways that resist a simple grand total. So I am not telling you that physicists have weighed the universe and found it weighs nothing. I am telling you something more modest and, I think, more interesting. The accounting at least permits a universe to balance to zero, which means the deepest reason we thought something could not come from nothing, the conservation of energy, may not actually forbid it after all. The door we thought was locked may have been open the entire time, but an open door and a balanced budget still do not tell you who walked through it or what wrote the first entry in the ledger. A balance sheet that sums to zero explains why creating a universe need not break the books. It does not explain how the transaction actually happened, what process took a perfect zero and split it into a roaring cosmos of plus and minus. For that, balancing the energy is not enough. We need a mechanism. We need something that can take nothing, or very nearly nothing, and actively bring a universe into being. And remarkably, the physics of the very small, the quantum mechanics we met a moment ago, contains exactly such a mechanism. It is a process in which things cross barriers they have no business crossing, in which a universe might quite literally tunnel its way into existence, is less than break time, equals 1s, is greater than number, Part 6. A universe tunnels into being. To understand the next idea, the one in which an entire universe comes into being through a quantum process, you first need to understand one of the most genuinely magical seeming effects in all of physics. It is called quantum tunneling, and despite how strange it sounds, it is happening inside you and around you every second of your life. Let me describe it with a simple picture. Imagine a ball sitting in a valley with a hill on either side. In the ordinary world, the world of classical physics, that ball will stay in the valley unless you give it enough energy to roll all the way up and over a hill. If it doesn't have enough energy to reach the top, it can never get to the other side. The hill is a barrier, and the rule is absolute. Not enough energy, no crossing, ever. But the quantum world does not obey that rule. In quantum mechanics, a particle is not a tiny solid ball with a definite position. It is described by a wave of probability, a smear of possibility spread out across space. And when that wave of possibility meets a barrier it does not have the energy to climb, something extraordinary happens. The wave does not simply stop at the barrier. A small part of it leaks through to the other side, which means there is a real, calculable chance that the particle will simply appear on the far side of a wall it could never have climbed over, as if it had dug a tunnel straight through. It did not go over the barrier. It did not go around it. It went through it by sheer quantum possibility. This is not a theoretical curiosity. Quantum tunneling is why the sun shines, because hydrogen nuclei tunnel through the barrier that would otherwise keep them apart and fuse together. It is why the memory chips in your phone can hold information. It is one of the most well-established effects in physics, even though it violates every instinct we have about how solid objects behave. Now, in the year 1982, a physicist named Alexander Vilenkin asked a question of staggering ambition. What if the universe itself could tunnel? What if, instead of a particle tunneling through a barrier in space, the entire universe could tunnel into existence from a state of no space and no time at all? Vilenkin worked through the mathematics of a tiny closed universe, a universe of zero radius, zero size, and he found that the equations described something remarkable. Such a universe could quantum tunnel through a barrier and emerge on the other side at a small but finite size, already expanding, already carrying within it the conditions for everything that would follow. He called it tunneling from nothing. And the nothing here is more radical than the seething vacuum we discussed before. In Vilenkin's picture, the nothing is a state with no classical space and no classical time whatsoever. There is no stage. There is no clock. There is only the quantum possibility, governed by the laws of physics, that a universe could appear. I want to make this as vivid as I can, because the language we normally use will mislead you. When we say the universe began, you instinctively imagine an explosion happening at some location at some moment, but that is not what this describes at all. There was no location for it to happen in, because space itself came into being with the universe. There was no prior moment at which it happened, because time itself came into being with the universe. It was not an explosion in space. It was the appearance of space. It was not an event in time. It was the beginning of time. The universe did not arrive somewhere. The somewhere arrived with the universe. This is so far outside everyday experience that our words almost break trying to hold it, and yet the mathematics is perfectly calm about the whole affair. Around the same time, working from a different angle, Stephen Hawking and James Hartle proposed an idea that has become known as the no-boundary proposal, and it is one of the most elegant ideas in the history of cosmology. They asked what happens to time as you approach the very beginning, and their proposal was that as you go back toward the origin, time gradually stops behaving like time and begins to behave more like another dimension of space. The sharp distinction between time and space softens and then disappears entirely. The consequence is profound. If time becomes space-like near the origin, then there is no sharp first instant, no edge, no boundary, where everything suddenly switched on. Hawking captured this with an analogy I find genuinely comforting, and it is the same one I want to leave with you as the thread of the whole evening. Asking what came before the Big Bang, he said, is like asking what is south of the South Pole. The South Pole is a perfectly real place. You can stand on it, but there is no such thing as south of it. The question is not unanswered. It is malformed. You have simply run off the edge of where the concept applies. In the no-boundary picture, the universe is finite in the past, but has no beginning edge, the way the surface of the Earth is finite, but has no edge you could fall off. These two ideas, Vilenkin's tunneling from nothing and Hawking and Hartle's no-boundary proposal, agree on something important and disagree on something equally important, and both halves of that are worth your attention. Where they agree is that there need be no classical singularity, no broken equation point of infinite density, and that the universe can, in some sense, be self-contained, requiring nothing outside itself to bring it about. Where they disagree is in the fine mathematical details, and the disagreement is real and unresolved. The two proposals are built on different ways of adding up quantum possibilities, and they produce different predictions, for instance, about the likely value of the energy of empty space. More than that, in the year 2017, a group of physicists, including Neil Turok, Job Feldbrugger, and Jean-Luc Leyners, published a serious challenge to the no-boundary proposal, arguing that when you do the mathematics with full care, it does not produce a smooth, well-behaved universe like ours at all, but rather predicts wild, uncontrolled fluctuations that would tear any orderly cosmos apart. The defenders of the no-boundary idea pushed back, and the argument continues to this day. This is not settled science. This is the living edge of the field, where some of the finest minds alive disagree about the mathematics of the first instant. And I want to be very clear about what kind of claim all of this is, because the honesty matters more than the spectacle. These are mathematical proposals about what physicists call the wave function of the universe, attempts to write down a quantum description of the cosmos as a whole, and ask what it implies about the beginning. They are not things we have observed. No one has watched a universe tunnel into being. No telescope has photographed the no-boundary. These are some of the most serious and careful speculations in all of science, but speculations at the frontier is exactly what they remain. So mark them clearly in your mind as the leading edge of theory, not as established fact. But here is the thread I want to pull tight before we move on, because it is the quiet payoff of this entire act. Even here, in the most literal and radical version of From Nothing that physics has ever managed to write down, the nothing still contains something. Vilenkin's nothing has no space and no time, yes, but it still has the laws of quantum mechanics. It still has the rules that make tunneling possible. There is no version of this story, not one, in which the universe arises from a nothing that is truly and absolutely empty of all law and all structure. The laws are always already there, doing the work, even when everything else is stripped away. Which brings us back to that uncomfortable truth from earlier. Physics can take us astonishingly close to nothing, closer than anyone a century ago would have dreamed possible. But it always carries its laws with it, like a traveller who can journey to the edge of the map, but can never quite step off it. The tunneling universe and the no-boundary universe both emerge at roughly the Planck size, that almost inconceivably tiny scale, and then something has to take that quantum speck and blow it up into a cosmos large enough to hold 2 trillion galaxies, and do it in a fraction of a heartbeat. That something is the most violent and creative process the universe has ever undergone. We call it inflation. And inflation hides a secret that is about to reopen the entire question of whether there was ever truly a beginning at all. Is less than break time equals 1s. Is greater than number part 7. The engine that made the universe huge. So far we have spent our time on the first word of our question, the word nothing, and we have watched it transform from an empty void into a seething quantum sea that balances perfectly to zero and can tunnel a universe into being. Now we turn to the second word, the word start. And to do that, we need to understand what happened in the instant immediately after that quantum beginning. Because something extraordinary took a microscopic speck and turned it into the universe we see. And the story of that something is going to make the very idea of a single, clean start begin to wobble. In the year 1980, a young physicist named Alan Guth was wrestling with a few stubborn problems in cosmology, puzzles about why the universe looks the way it does, and he stumbled onto an idea that would reshape the entire field. The idea was that in the very first sliver of a second of the universe's existence, long before the first atom formed, the universe went through a phase of expansion so violent, so explosive, that it almost defies description. We call it cosmic inflation, and the numbers involved are so extreme that I have to slow down and unpack them carefully, because they are the kind of numbers that lose all meaning if you just say them quickly. During inflation, the universe is thought to have doubled in size, and then doubled again, and again, and again, over and over, in a runaway cascade. In a span of time, around 1/10 million trillion trillionth of a second, the universe expanded by a factor of at least 10 to the 26th power. Let me try to make that quantity feel like something. 10 to the 26th power is a 1 followed by 26 zeros, which is roughly 100 trillion trillion. Imagine something the size of a single atom suddenly swelling, in far less than the blink of an eye, to be larger than an entire galaxy. That is the scale of inflation. A patch of space, far smaller than a proton, was stretched almost instantaneously to something the size of a grapefruit or larger, and from that grapefruit grew everything we can see. And yes, this expansion happened faster than the speed of light, which sounds like it should be forbidden, but nothing was moving through space faster than light. It was space itself that was expanding, and space is under no obligation to obey the cosmic speed limit. The limit applies to things travelling through space, not to the stretching of the stage itself. Now, you might reasonably ask why anyone believes such an outrageous thing happened. And the answer is that inflation solves several problems that otherwise have no good explanation. When we look at the cosmic microwave background, that afterglow we met earlier, we find it is astonishingly smooth, almost the same temperature in every direction, even between regions on opposite sides of the sky that, in the conventional story, should never have had time to come into contact and even out their temperatures. Inflation explains this beautifully. Those regions were once tiny and close together, in contact, sharing the same temperature, and inflation then flung them billions of light years apart while preserving their sameness. It also explains why space appears so remarkably flat, and why we don't see certain exotic relics that older theories predicted. For all its extravagance, inflation does real explanatory work, which is why it became the leading picture of the early universe. There is more to the case than tidiness, too. Inflation makes specific predictions that have actually been tested against the sky. It predicts that the tiny temperature ripples in the cosmic microwave background should have a particular pattern, a specific balance of larger and smaller variations, and when the Planck satellite measured those ripples in exquisite detail, the pattern matched what inflation predicted with remarkable precision. Inflation also predicts something even more dramatic, which physicists are still hunting for today. The same violent stretching that magnified quantum fluctuations should also have produced ripples in the fabric of space-time itself, primordial gravitational waves, faint echoes of the first instant rolling through the geometry of the cosmos. We have not yet caught these directly, and a famous announcement in the year 2014 that claimed to have found them turned out to be dust in our own galaxy, masquerading as the signal. But the search continues, and if we ever do detect those primordial waves, we will be reading a message written in the very first sliver of a second of the universe's existence. That is how seriously inflation is taken. It is not just a story that explains what we see. It is a theory that sticks its neck out and tells us what else to go looking for. But here is the part that ties directly back to our central thread, and it is the part I find most beautiful. What was it that drove this inflation? What provided the engine, the fuel? The answer is a high-energy version of the very thing we spent all of Act 2 discussing. Inflation was powered by a vacuum, by the energy of empty space in a peculiar high-energy state. The seething nothing, the quantum vacuum with its restless energy, is precisely what drove the universe to inflate, and this connects two halves of our question in the most elegant possible way. Remember those virtual particles, those quantum fluctuations flickering through the vacuum? During inflation, those microscopic fluctuations were stretched along with everything else, blown up from quantum specks to enormous scales. And those stretched out fluctuations became the seeds of everything. The tiny ripples we see in the cosmic microwave background, the faint variations in temperature across the sky, are quantum fluctuations from the first instant, frozen and magnified to cosmic size. And those ripples are where galaxies later formed, which means that every galaxy, every star, every planet, and every person is, in the end, a quantum fluctuation of the vacuum that inflation stretched until it became real. The somethings of the universe grew from the restless nothing. And yet, inflation carries a secret, a strange and almost mischievous property that is going to drive the rest of our story. Inflation is so violent, so thorough in its stretching, that it erases the evidence of what came before it. Whatever conditions existed prior to inflation, whatever the universe was tunneling or bouncing or emerging from, inflation smooths it all away, flattens it, dilutes it into invisibility. It is as if the universe, in its first instant, took an enormous eraser to its own origin story. So inflation is the bridge between the seething nothing of the vacuum and the start of everything we can see, the process that turns a quantum possibility into a cosmos. But by smoothing over its own beginnings, inflation also hides whether that start was truly the first start or merely the latest in a longer story. And once you start asking that question, once you ask whether inflation might have been going on before our patch of universe began, you arrive at an idea so strange that it suggests our universe may never have started at all. Is less than break time equals 1s is greater than number. Part 8. Maybe it never started. Here is where the word start truly begins to come apart in our hands. We have been speaking of inflation as the violent burst that launched our universe. But in the 1980s, physicists including Andrei Linde, Alexander Vilenkin, and Alan Guth himself realized something unsettling about how inflation behaves. Once it starts, it may be almost impossible to stop completely. And that single insight opens a door onto a picture of reality so large that it makes a single universe look like a single grain of sand on an endless shore. The reasoning goes like this. Inflation is driven by that high-energy vacuum state, and that state is supposed to decay, to come to an end, allowing normal expansion to take over and matter to form. That ending is what we call the Big Bang in our region, the moment inflation stopped and the hot, particle-filled universe began. But because inflation is a quantum process, it does not end everywhere at the same time. It ends in some places while continuing in others, and the regions where it continues are inflating so fast, doubling and redoubling so violently, that they quickly come to dwarf the regions where it has stopped. So you get a picture where inflation is ending here and there, in isolated pockets, each pocket becoming what we would call a universe, a bubble where the violence has calmed and matter and galaxies can form. But the space between and around these bubbles keeps right on inflating, endlessly spawning new bubbles forever. This is called eternal inflation. Now think carefully about what this does to our question, because it is a genuine demolition of the word start. In the picture of eternal inflation, our Big Bang, the event we have been treating as the origin of everything, is demoted. It is no longer the beginning of all that exists. It is merely the moment that inflation happened to stop in our particular bubble. It is the beginning of us, of our local patch, but not the beginning of everything. Beyond our bubble, the larger structure has been inflating and budding off new universes for an unimaginably long time, perhaps forever. There may be no ultimate beginning at all. There may be no first bubble. Something was always inflating, always there, endlessly giving birth to new regions, and our universe is just one of countless others, each pinched off from the eternal froth, like a bubble rising in a boiling pot that never stops boiling. I want to pause on how this reframes our central question, because it is the cleanest example yet of the move we keep watching physics make. We asked whether the universe started from nothing. Eternal inflation answers, in effect, that our universe did not start from nothing, it pinched off from something that was already there and busily inflating. The nothing recedes again, replaced by an eternal, self-renewing somewhere. And of course, this raises the obvious question, which honest physicists do not dodge. If inflation is eternal into the future, was it also eternal into the past? Did the whole budding structure itself have a beginning? Here, the picture gets murky and contested. There is a result known as the Border-Guth-Vilenkin theorem, named for the three physicists who proved it, which suggests that an inflating universe, even an eternally inflating one, cannot be extended infinitely far into the past. It too seems to require some kind of past boundary, some beginning to the inflation itself. So, eternal inflation pushes the question of the start backward, perhaps enormously far backward, but it may not eliminate it entirely. It relocates the mystery rather than dissolving it. This idea of an endless multiverse, with countless bubble universes, each potentially having different physical constants, different strengths of gravity, different masses for their particles, is one of the most debated ideas in modern physics. And I want to be careful to flag it clearly. We cannot see other bubble universes. They are, by their nature, beyond our horizon, forever out of reach of any telescope. So, eternal inflation, for all that it follows naturally from theories we take seriously, remains unconfirmed, a powerful idea rather than an observed fact. Some physicists embrace it. Others find the unobservable multiverse a step too far, a place where physics shades into something harder to test. And one of those skeptics was, perhaps surprisingly, Stephen Hawking himself, right at the very end of his life. In the year 2018, just before he died, Hawking published his final scientific paper, written with his longtime collaborator Thomas Hertog, and in it, the two of them pushed back hard against the runaway multiverse of eternal inflation. Using tools from string theory and from the idea of holography, they argued that the multiverse predicted by standard eternal inflation was far too wild, far too varied, an infinite and unmanageable sprawl of radically different universes. Their alternative was a multiverse that was much smaller, much smoother, and far more finite, with universes that resemble one another rather than spanning every possibility. In their picture, the cosmos was closer to a single, comprehensible universe than to an infinite chaos. And once again, in reaching for this, they did the same thing the no-boundary proposal had done decades earlier. They reached for a beginning where time itself becomes less fundamental near the origin, smoothing away the sharp edge of the start. It was a fitting final act, for a man who had spent his life thinking about the beginning of time, arguing, with his last breath of physics, that the beginning was gentler and more unified than the wild multiverse suggested. Yet whether Hawking and Hertog were right, or whether the sprawling multiverse is real, remains an open and active dispute. What both sides share, though, is the same quiet erosion of our original question. In a multiverse, large or small, our beginning was local, a bubble pinching off from something already in motion, and the grand from nothing start retreats ever further out of view. But the multiverse is not the only way to make the beginning disappear. There is an older, and in some ways simpler idea, one that says the universe did not begin at all because it bounced, is less than break time equals 1s is greater than. Number part 9. Maybe it bounced. Let us return for a moment to that broken equation, the singularity, the place where general relativity threw up its hands and screamed infinity. We said that the infinity was an error message, a sign that we needed new physics to take over at the very beginning. Well, suppose we take that seriously and ask what the new physics might actually do to that moment. One of the most natural and appealing answers is that the new physics removes the singularity entirely and replaces it with something far gentler. Not a beginning, but a bounce. Not a first moment, but a turning point in a story that was already underway. The intuition behind a bounce is this. The singularity appears because, in classical general relativity, there is nothing to stop matter from collapsing all the way down to a point of infinite density. Gravity just keeps pulling, harder and harder, with nothing to push back. But what if, when you get down to extreme enough densities, something does push back? What if gravity, at the smallest scales, stops being purely attractive and becomes repulsive, slamming on the brakes before the collapse reaches infinity? Then a universe contracting under gravity would not crunch down to a singularity. It would squeeze to some enormously high but finite density, and then rebound, exploding outward in what would look, from the inside, exactly like a Big Bang. Our beginning would actually be the rebound of a previous universe's ending. The Big Bang would be a big bounce. Several different lines of physics arrive at versions of this idea, and I find it worth meeting a few of them, because their variety tells you how seriously the bounce is taken. One approach comes from a field called loop quantum cosmology, which grows out of an attempt to quantize gravity itself, to apply quantum rules to the fabric of space-time. In this picture, space cannot be subdivided infinitely. There is a smallest possible chunk of space, a fundamental graininess. And when you try to cram matter down toward that smallest scale, the quantum nature of geometry creates a powerful repulsion, a kind of pressure from the structure of space itself that forbids the singularity and forces a bounce. The universe, in this view, has a previous chapter, a contracting phase that collapsed down, bounced off the quantum floor of space, and is now the expansion we find ourselves living in. Another approach comes from string theory, in a model sometimes called the ekpyrotic or cyclic universe, developed by physicists including Paul Steinhardt and Neil Turok. Here the picture is genuinely cinematic. Our three-dimensional universe is imagined as a kind of membrane, a brain, floating in a higher dimensional space, and there is another such membrane nearby. These two membranes drift toward each other, collide, and bounce apart, and the colossal energy of that collision is what we experience as the Big Bang. The membranes then drift together again over enormous stretches of time, collide again and bounce again, in a cycle that could repeat endlessly into the past and the future. In this story, there were Big Bangs before ours, and there will be Big Bangs after ours, each one a collision in an eternal rhythm. And then there is perhaps the most poetic version of all, an idea from the brilliant and unconventional mind of Roger Penrose, the same Penrose who helped prove the singularity theorems decades earlier. He calls it conformal cyclic cosmology. Penrose imagines that the universe goes through an infinite sequence of enormous epochs, which he calls aeons. Each aeon begins with a big bang, expands, forms galaxies and stars, and then, over almost incomprehensible stretches of time, fades into a cold, empty, dark future where everything has decayed and only thinly spread radiation remains. And here is Penrose's leap. He argues that this cold, empty end state of one aeon, where there is no matter left to define any scale of size or time, is mathematically identical to the hot, dense, smooth beginning of the next aeon. The end of one universe becomes, through a kind of rescaling, the Big Bang of the next. Death and birth become the same event seen from two sides. Penrose has even claimed to find evidence for this in the cosmic microwave background, faint concentric circles he calls Hawking points, which he interprets as the signals of supermassive black holes from a previous aeon. I have to flag this clearly, though. Most cosmologists are profoundly skeptical of these claimed circles, and the evidence is very much disputed. The idea is beautiful, but it sits well outside the mainstream consensus. It is worth pausing to ask why so many serious physicists are willing to entertain these bounce ideas at all, rather than dismissing them as wishful thinking. The honest reason is that the bounce is not chosen for its elegance. It is forced on us by the failure of the singularity. Once you accept that the infinite density point at the beginning is a symptom of a broken theory, you are obliged to ask what the corrected theory does to that moment, and a bounce is one of the most natural things a corrected theory can produce. There is a real difficulty, though, one that the critics raise with force, and fairness demands that I mention it. It is the problem of disorder. Our universe began in an exquisitely ordered, low disorder state, which is precisely why time has a direction and why the future looks different from the past. But disorder, in physics, only ever tends to increase. So if there was a previous universe that collapsed and bounced into ours, its disorder should have carried over, and our universe should have begun far messier than it did. Explaining how a bounce can reset the books, how the contracting phase can hand over a clean, orderly universe rather than a chaotic one, is one of the hardest unsolved puzzles these models face. Penrose's rescaling is one bold attempt to answer it, and other models have their own, but none has fully closed the case. So the bounce is appealing and well motivated, but it is not free of trouble, and the trouble is real. What all of these bounce models share, beneath their different mathematics, is a single radical implication for our question tonight, and it is the cleanest answer we have heard so far. If the universe bounced, then it did not start from nothing, because it did not start at all. There was always a before. There was a previous universe, or a previous aeon, or an endless cycle of collisions, stretching back into a past that may have no beginning. The Big Bang, in this view, was never a creation event. It was a transition, a phase change, a turning point in an ongoing story. And so the word start, the second dangerous word in our title, reveals itself as possibly the biggest illusion of all. We assumed the universe began. The bounce models whisper that perhaps nothing ever truly begins, that the cosmos simply changes from one form to another, forever. I should be honest, as always, that these bounce models are serious and well motivated, born from the genuine need to fix that broken singularity, but none of them has been confirmed by observation, and the most dramatic claimed evidence, like Penrose's circles, remains contested. Still, the idea refuses to go away, and in the last few years it has taken a startling new turn. Because some physicists are now arguing that we do not just live in a bounced universe. We may be living inside a black hole. Is less than break time equals 1s is greater than number. Part 10. Maybe we're inside a black hole. Of all the ideas we will meet tonight, this next one is the freshest, the strangest, and in some ways the most dizzying, and it has been making real waves in physics in just the last year or two. The proposal is this: our entire universe, everything we can see, every galaxy and every atom, may be sitting inside the interior of a black hole that exists in some larger, parent universe. Our Big Bang, in this picture, was not the beginning of all things. It was what happened on the inside when something collapsed into a black hole on the outside. To understand how anyone could take this seriously, we need to connect it to the bounce we just discussed. Think about what happens when a giant star runs out of fuel and collapses under its own gravity. In standard physics, that collapse runs all the way down to a singularity at the center of a black hole. The same kind of broken equation infinity we met at the beginning of the universe. But suppose, just as in the bounce models, that something stops the collapse before it reaches infinity. Suppose the matter falling inward squeezes down to an enormous but finite density and then rebounds. From the outside, you would still see a black hole, a region from which nothing escapes. But on the inside, that rebound, that bounce, might look exactly like a new universe exploding into being and expanding. Every black hole, in this view, might give birth to a baby universe inside itself, a universe whose inhabitants would experience their birth as a Big Bang and would have no way of knowing they were living inside the collapsed remnant of a star in some greater cosmos. One of the people who has championed this idea for years is the physicist Nikodem Poplawski, and his version rests on a property of spacetime called torsion. The idea draws on an extension of Einstein's general relativity, sometimes called Einstein-Cartan theory, which takes seriously the fact that particles have spin, an intrinsic quantity of rotation. In Poplawski's mathematics, the spin of matter at extreme densities produces a twisting of spacetime, the torsion, and that twisting creates a powerful repulsive effect at the smallest scales. That repulsion, exactly like in the bounce models, halts the collapse and triggers a rebound. So when matter collapses into a black hole, it does not vanish into a singularity. It bounces, and the bounce inflates into a new universe on the other side. We could be the children of a collapsing star. And then, in the year 2025, this whole circle of ideas gained fresh momentum from a new model developed by Enrique Gastañaga and his colleagues at the University of Portsmouth, published in a serious physics journal. They combined general relativity with quantum principles, in particular with the rule that prevents matter from being squeezed together without limit, and they argued that gravitational collapse need not end in a singularity at all. Under the right conditions, they found, collapse ends in a bounce, and that bounce could be the origin of an expanding universe just like ours. They have called it, in effect, a black hole universe model, and it reframes our Big Bang not as a creation from nothing, but as the rebound at the core of a collapse. What makes this more than just elegant mathematics is that it may come with an observational hint, and this is where it gets genuinely tantalizing, though I have to be careful with you about how strong the evidence really is. The James Webb Space Telescope, our most powerful eye on the early universe, has been surveying distant galaxies and measuring which way they spin. And some analyses of that data have reported something unexpected. More galaxies appear to be rotating in one direction than the other. In a universe with no preferred direction, you would expect a roughly even split, half spinning clockwise, half counterclockwise. A lopsided result would suggest that the universe as a whole has a net rotation, a built-in spin, and here is the connection. If our universe were born inside a black hole, and if that black hole were itself rotating, which most real black holes do, then the baby universe inside might inherit that spin. A net rotation of the cosmos is exactly what you might expect if we were born inside a spinning black hole. Now, I must stress, this is contested. The reported asymmetry might be a statistical fluke, or it might come from subtle biases in how we observe and classify distant galaxies, perhaps even from the way our own galaxy's motion affects what we see. It is a hint, an intriguing whisper, not a proof. But it is the kind of whisper that makes physicists sit up. And the story has grown another branch even more recently. In work appearing around 2026, some physicists have suggested that black holes, which formed before our Big Bang and survived a cosmic bounce, could make up the mysterious dark matter that holds galaxies together, the invisible stuff that outweighs all the visible matter in the universe by a factor of several. These relic black holes, left over from a previous phase, would drift through the cosmos as dark matter, and they might even help explain another puzzle the James Webb Telescope has uncovered: the existence of surprisingly massive, bright galaxies, sometimes called little red dots, that appear far earlier in cosmic history than they should. It is a remarkable web of connections, linking the origin of the universe, the nature of dark matter, and the puzzles of the earliest galaxies, all through the single idea of a bounce. I will be honest one more time, because it matters. This is frontier science, exciting and backed by real papers and real calculations. But it is not consensus, and the observational evidence is still preliminary and hotly debated. Yet even as speculation, it delivers the most vivid possible version of our central thread, and I want you to feel the full weight of it. If we truly live inside a black hole, then our nothing, the void we imagined before our beginning, was in fact a dying star in a parent universe. What we call the origin of everything was, on the other side of the horizon, just another Tuesday, a star collapsing, as stars do. And from that vantage point, the question, did the universe start from nothing, becomes almost meaningless, because whether you call our beginning a creation from nothing or the inside of a black hole depends entirely on which side of the horizon you happen to be standing on. The same event is a beginning from within and an ending from without. Nothing and beginning turn out to be relative, points of view rather than absolute facts. And that thought, that the answer depends on where you stand, is going to lead us to the strangest possibility of the entire evening. Because maybe the reason we cannot answer the question is not that the answer is hidden. Maybe it is that the question, the way we have been asking it all along, was never quite a real question to begin with. Is less than break time equals 1s is greater than number. Part 11. What's north of the North Pole? We have spent the whole evening trying to answer a question, and we have watched it twist and slip away from us at every turn. So now, I want to try something different. Instead of asking what the answer is, let us ask whether the question is even well formed. Because there is a possibility, lurking underneath everything we have discussed, that the question, did the universe come from nothing, is not a hard question waiting for a clever answer. It may be a malformed question, one that quietly assumes something that simply is not true. Look closely at the words again. When we ask what came before the beginning, or where the universe came from, we are using words that smuggle in an assumption. The word before assumes there was a time prior to the beginning. The word from assumes there was a place or a state the universe emerged out of. In other words, our question assumes that time was already running before the universe existed, ticking away in some empty waiting room, and that the universe then appeared within that pre-existing flow of time. But what if time itself is not fundamental? What if time, like temperature, is something that only emerges when you have enough stuff arranged in the right way and did not exist in some prior, more basic state of reality? This is not a wild guess. It is a serious and growing direction in physics. There are good reasons to suspect that time is not a fundamental ingredient of reality, but an emergent one. Some physicists tie the flow of time to entropy, to the relentless increase of disorder, suggesting that the very sense of time moving forward is really just the universe becoming more disordered, and that without that increasing disorder, there would be no arrow, no direction, no flow at all. Others suspect that time emerges from the quantum connections between things, from entanglement woven out of relationships rather than existing on its own. And if any of these are right, then there was no time before the universe, because time came into being with the universe, exactly as Vilenkin and Hawking suggested in their different ways. And if there was no time before the universe, then the word before, in the phrase before the universe, points at nothing. It is an empty word. This is where Stephen Hawking's beautiful analogy comes back to close the loop, the one I promised would carry us through the whole night, asking what is north of the North Pole. The North Pole is a perfectly real, perfectly ordinary place on the earth. You can stand there, you can plant a flag, but if you ask what lies north of it, the question has no answer. Not because we lack the information, not because the answer is hidden somewhere we cannot reach, but because north simply runs out at the pole. There is no more north to be had. The question is built on a geometry that does not extend that far. And in exactly the same way, asking what came before the beginning of time may be a question where before runs out, where the concept simply has no more room to apply. The question is not unanswered. It is, in the most precise sense, malformed. It points off the edge of a map and asks what the territory looks like there when there is no there. And just to make sure we never get too comfortable with the idea that we even know what nothing is, consider one more recent piece of work. In the year 2025, researchers used a powerful quantum machine, a device built from more than 5,000 quantum bits, to simulate a process called false vacuum decay. The idea behind it is unsettling. Our vacuum, the seething nothing we have discussed all night, might not actually be the true lowest energy state of reality. It might be a false vacuum, a state that looks stable, that has looked stable for nearly 14 billion years, but which could, in principle, suddenly decay into an even lower state, releasing energy and rewriting the laws of physics in an expanding bubble. If that is true, then even our nothing is provisional, a temporary resting place, rather than the bottom of everything. The very floor we have been standing on all evening may itself be a kind of illusion, one more level that something deeper sits beneath. So here, at the end of our search, we find that the question may dissolve rather than resolve. Not answered with a yes or a no, but quietly revealed to rest on assumptions, a before, an empty nothing, a clean beginning, that do not survive close inspection. And if the start of the universe came with time rather than within it, then the universe did not come from nothing after all. It came with time itself, and the question of what was before folds gently in on itself, like a road that curves around until it meets its own beginning, is less than break time equals 1s, is greater than number, part 12. So did it. So let us sit together now, at the end of the night, and gather up everything we have found. We set out with a question that a child could ask in 5 simple words. Did the universe start from nothing? And what we have discovered, after walking this long road together, is that nearly every word in that question turned out to be unstable, shifting under our feet the moment we put any weight on it. We did not so much answer the question as watch it transform in our hands into something far stranger and far more honest. Consider what became of the word nothing. We began imagining it as an empty void, a black stage with the lights off, a perfect absence. And we discovered that the only nothing physics can actually study is the quantum vacuum, a seething sea of fluctuating energy where particles flicker in and out of existence, where 2 metal plates are pushed together by the pressure of empty space, where light itself can be coaxed out of the dark. We discovered that this nothing has so much energy that a whole universe might come out of it for free, because the positive energy of all matter may be exactly cancelled by the negative energy of gravity, leaving a grand total of zero. We discovered that a universe and a void may carry the very same balance sheet, the same zero charge, the same zero momentum, the same zero total energy, so that going from nothing to everything is less a creation than a separation of zero into matched halves of plus and minus. The nothing in our title was never empty. It was always already something, always already humming with law and energy. And consider what became of the word start. We began imagining it as a single, sharp first moment, a point of beginning, and we discovered that the point was a singularity, which is to say, a broken equation, an error message marking the place where our finest theory of gravity gives up. We watched physicists try to replace that broken point with gentler ideas, a universe tunneling into being from a state with no space and no time, yet still governed by quantum law. A no-boundary universe where time rounds off smoothly near the origin, so there is no first instant at all, the way there is no edge to the surface of the Earth. An eternal inflation in which our Big Bang is merely the moment our local bubble stopped inflating, while the larger structure goes on budding new universes forever. A bounce, in which our beginning was the rebound of a previous universe's ending. A black hole interior, in which our entire cosmos is the inside of a collapsed star in some parent universe, and our Big Bang is just the view from within. In every one of these pictures, the clean, sharp start dissolves into a transition, a handoff, a phase change in a story that was already underway. So here is the honest synthesis, the place where the whole thread finally comes together. The universe did not come from nothing, so much as it taught us that nothing was never empty, and that beginnings may not be where reality starts. Every time we reached for the ultimate origin, for the true first cause, for the genuine nothing, we found that something was already there, a law, a field, a quantum vacuum, a previous phase, a parent universe. The laws of physics, doing their quiet work, are present in every single one of our deepest descriptions of the beginning, and we have never once managed to write down a true account of the universe arising from a nothing that contained no law and no structure at all. And there may be a reason for that, a reason built into the very nature of what we are doing. Physics describes the universe by finding its laws, but the instant you have a law, you have a kind of something. So, when we try to use physics to reach all the way back to absolute nothing, we always find that we have carried a law along with us. Like a traveller who journeys to the very edge of the map only to discover that the edge keeps receding because the map travels with them. We may simply never be able to reach the true first question because every physics we can write already assumes that something exists. And this is the point where physics, having taken us further than anyone a century ago could have dreamed, hands the question over to philosophy, and does so with a certain grace. Because beneath everything we have discussed lies the oldest version of the question, the one the philosopher Gottfried Leibniz asked more than 300 years ago, and the one that no equation has ever fully silenced. Why is there something rather than nothing? Why is there anything at all, rather than just blank, lawless absence? Physics can explain how a universe might emerge from the quantum vacuum. It can balance the energy books to zero. It can replace the beginning with a bounce. But it cannot quite explain why there is a quantum vacuum in the first place, why there are laws at all, why the great zero ever bothered to split itself into something and its opposite. Some people hear that question and reach for a first cause, for a creator. Others hear it and conclude that the question itself is the malformed one, that something is simply the way reality is, with no further explanation required or possible. I am not going to tell you which of those to believe, because that choice sits in a place where physics, for all its power, falls quiet and respectful, and where each of us has to find our own footing. But I will leave you with one last thought, and I want you to carry it with you as you drift off tonight. We have spent this whole evening talking about the universe, about its origin, about whether it came from nothing. But you are a part of that universe. The atoms in your body, the carbon in your cells, the oxygen moving through you as you breathe slowly in the dark, were all forged in the hearts of stars and scattered across space long before the Earth existed. You are, quite literally, a piece of the universe that has arranged itself into a pattern complex enough to wonder where it came from. And the very same uncertainty that surrounds the origin of the cosmos surrounds your own. You, too, are a brief and improbable arrangement of the same restless vacuum, the same balanced zero, awake for a single moment in an immense stretch of time, asking the oldest question there is. So perhaps the strangest fact of all is not that the universe might have come from nothing. Perhaps the strangest fact is simply that there is something at all. That instead of a blank, lawless, eternal absence, there is a cosmos of 2 trillion galaxies, and starlight, and time, and breath. And that a small, warm, conscious fragment of it, lying here in the quiet of the night, is wondering about the rest of it, and finding, in that wondering, that it is not separate from the mystery at all. It is the mystery, briefly, looking back at itself,